Now let's turn our attention to another comparison test, which is known as the Now let's turn our attention to another comparison test known as the limit comparison test. Now it's a bit different from the direct comparison test. It's a little more difficult to kind of wrap your head around as to exactly why this works. But it is a very nice test. It's very straightforward to apply. Usually you can solve most of it with just L'Hopital's rule. But here's how it works. So you have two different sequences, and you know that they're both positive for all values. And the idea is that if the limit of the quotient of those two series, and it doesn't matter if a sub n is the known series or b sub n is the known series, it makes no difference whatsoever. You just divide the two, and if you get a finite real number that's not zero, then that tells you that both series either converge or both diverge. And there's actually two other parts to this. If the result of the limit is zero and your known series converges, then your questioned series will also converge. Or if the limit is infinity and the known series diverges, then that proves that the remaining series, the questioned series, also diverges. But to be honest, the only real part of the limit comparison test that I use is this first part. In my opinion, it's a very easy and clean result. It generally only relies on L'Hopital's rule. And then these are kind of like nuances that can work, but usually if I end up with zero or infinity for the limit comparison test, I just ultimately just say the test fails and then go work with a different one, rather than trying to remember these additional rules here. So let's take a look at the previous example that didn't work with the direct comparison test and see if we can get a result with the limit comparison test. So with the limit comparison test, here's what we do. We also need something to compare to. So we state what we're comparing to. In this case, it's not going to be any different. We are going to still compare to 1 over n squared. That's the closest thing to what we have in our, I'll call this our unknown and this our known series. So b sub n then is a p series with p is equal to 2, which is greater than 1, so we know that this converges. Okay, now the test is to find an infinite limit of the quotient of these two series. And again, it doesn't matter which one's the numerator and which one's the denominator. You don't have to worry about that. So I will evaluate the limit as n goes to infinity of 1 over n squared minus 1 divided by 1 over n squared. And I just want to see if the value of this limit exists. All right, so changing this fraction into something simpler, what I'll do, I'll multiply by the denominator. So this would just be the limit as n goes to infinity of n squared over n squared minus 1, for which you can use L'Hopital's rule. That would just take a couple of steps and you'd be done. Or you can also use the rules for infinite limits with respect to rational functions and know that the degrees are the same in the numerator and denominator, so therefore this would go to the ratio of the leading term coefficients, which is positive 1, and that's not equal to 0 or infinity. So the test passes. So therefore, a sub n also converges by the limit comparison test. So let's take a look at an idea as to why this test might work. Okay, so the series that we're trying to learn about is 1 over n squared minus 1. And the series that we know is 1 over n squared. We started with n equals 2 because this resulted in division by 0 when n was 1. So that's fine. Okay, so when I hit update, all I'm seeing currently is just the sequence points of A, the one that we want to know about. So let's take a look at the sequence points of B. All right, so I could possibly zoom in a little bit here, see that a little bit better. So the blue one is sequence A, which is the unknown. So if I take a look at these as a function, all right, the red one is known to be going to 0 fast enough to converge. But the blue one, the unknown, is going slower than that. So that's why that inequality failed in the direct comparison test, because this one would need to be going to 0 faster than the red one in order for it to converge by the direct comparison. Okay, so let's remove those mappings. And let's take a look at what happens with the limit comparison test. So all this will do when I check this box is just take the elements of each of these one by one, take the y values and divide them. So it'll give me the ratio of those values. I need to scroll, there it is, okay. So for instance, if I took 0.33 divided by 0.25, it looks like I would get 1.33. All right, so that's what's happening. Just taking each of these and dividing them, and this is the result. Now, if you'll notice, the value of this limit comparison certainly is approaching a value. It's approaching 1. It's not running off to infinity or going to 0. So ultimately what that means is that this is going to happen whenever the two series in questions are going to 0 at about the same rate. All right, so it can be off by some. Generally speaking, this works really well for polynomial functions, whether or not your original series has a bunch of terms in it or not. It just compares to see if they're going to infinity at about the same rate, or going to 0, I should say, at about the same rate. And if they are, then this quotient of these values will go to a real number. If one of them is going to 0 exceedingly faster, or if one of them is going to 0 much slower, then this will either go to 0 or to infinity, and therefore we won't be able to get a result. So that's ultimately the idea behind the limit comparison. And I'll show you another one where we have this running to infinity, and you can kind of see how that works. But for now, that's the idea. All right, so our next example, we have a series n equals 1 to infinity of 1 over the square root of n plus 1. All right, so that looks very similar to a p-series. So I'm going to use a comparison test, and in this case the limit comparison test, and I'm going to compare that to the series from n equals 1 to infinity of 1 over the square root of n, which would be the same as n to the 1/2 power, which would be a p-series, with p equal to 1/2, which is less than 1, so it diverges. So I'm expecting the original series to diverge as well. So let's do the test. So that tells me to take a limit as n goes to infinity of let's just put the original series on top. So n to the 1/2 plus 1 over 1 over n to the 1/2. So then that's the limit as n goes to infinity of n to the 1/2 over n to the 1/2 plus 1. Now, with rational functions, you can make the conclusion that this would go to 1. If you weren't certain that that was the case here, you can always rely on L'Hopital's rule, because if you let n go to infinity, the numerator and denominator are certainly both going to infinity. So if we apply L'Hopital's rule, and this would be the limit as n goes to infinity, the derivative of the numerator would be 1/2 n to the negative 1/2. The derivative of the denominator would also be 1/2 n to the negative 1/2, because the derivative of 1 goes to 0. And that's great because these two terms cancel, and, well, even the halves cancel. So that tells me the result of this limit is 1, which is not 0, and is finite. So that's great. That tells me that the test passes, and therefore I can conclude that the original series also diverges by the limit comparison test. All right, let's try another. So use the limit comparison test to determine whether the series converges or diverges. If the test does not apply, state that. Okay, so this one looks suspiciously like a geometric series to me. So that's what we use when we do the limit comparison test to compare to. So you just want to pick what it looks closest to. So n equals 1 to infinity, and I'll compare this to 2/3 to the n. And again, this should be to the n minus 1, but I would also have to get this corrected to n minus 1. And the first few terms don't really matter, okay? So, well, they don't really matter in terms of convergence. If I was trying to figure out what this converged to, they would matter, but not in terms of whether it converges or not. So this is geometric. And the value of r is 2/3, which is less than 1. And when that's less than 1, it converges. All right, so we know this one converges. So then the test asks me to take a limit as n goes to infinity of the original series divided by the other series, so 2 to the n over 3 to the n. Okay, so this will be the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n times 3 to the n over 2 to the n. So just inverting and multiplying. Now what's nice is the 3 to the n's will cancel, but that's not necessarily the case in the other term. So I would have the limit as n goes to infinity 2 to the n plus 1 over 2 to the n, which I could use L'Hopital's rule and I think I would be done with. Or actually, I could do a little bit of algebra as well, more than one way in this case. 2 to the n over 2 to the n would be 1, and then 1 over 2 to the n would just be exactly that. And the nice thing is, as n goes to infinity, this would go to 0, so the value of the limit is going to 1, which of course is not 0, and is finite, so therefore we get a result. So because the known series converged, that tells me the unknown series also converges by the limit comparison test. All right, this next example, we have the series from 1 to infinity of the natural log of n divided by n squared. Okay, so probably the most likely choice that I would go with here, if I were to pick the limit comparison test, is to compare this to a p series of 1 over n squared. So n equals 1 to infinity, 1 over n squared. So that's a p series with p is equal to 2. So that's greater than 1, so therefore this converges. All right, and let's take a look and see if this can prove convergence. So we'll do our test here. And we want the limit as n goes to infinity, the natural log of n over n squared divided by 1 over n squared. Now, when I invert and multiply, I would have the natural log of n over n squared times n squared over 1. So that n squared cancels, and I'm really just left with the limit as n goes to infinity of the natural log of n. And the limit as n goes to infinity of the natural log of n, well, that certainly does grow very slowly, but it does continually grow and goes to infinity. So ultimately the test fails there. And those additional caveats on this, since the known series converges, we would have needed this limit to go to 0, and technically the test wouldn't have failed, but like I said, I really don't use those results. I would just switch and use a different test altogether. Now, this isn't to say that the limit comparison test isn't going to work, it's just maybe the thing that we compared to didn't apply. So when I have the natural log of n over n squared, I could kind of think of like this as n over n squared, which would be more like 1 over n. So possibly this actually diverges, and I would need to compare to the harmonic series to prove that. So let's give that a try. So let's try again, but this time let's compare to the series from n equals 1 to infinity of 1 over n, which is the harmonic series. Oops, I spelled that correctly there. Which diverges. Okay, so then the test would just again require to do a limit as n goes to infinity of natural log n divided by n squared over 1 over n. So then I have the limit as n goes to infinity of natural log n over n squared times n over 1. The n cancels one of those factors of n there. And then I'm looking at just the limit as n goes to infinity of the natural log of n divided by n, which I'm not particularly sure exactly what happens with that, but as n goes to infinity, both the numerator and denominator would go to infinity, so I can use L'Hopital's rule to try and get an idea. So if I use L'Hopital's rule, the derivative of the natural log of n is 1 over n. The derivative of n is 1. So this is essentially just 1 over n. And as n goes to infinity, that thing goes to 0, so therefore this limit goes to 0, which also tells me that the test fails. So it's just entirely possible that maybe the limit comparison test isn't the best one to use here. And perhaps let's take a look at this visually to see if we can understand why that is. Okay, so the series we're trying to find out about is the natural log of n divided by n squared. And we compared it to two different series. I think what I'll use here is maybe 1 over n squared. Maybe that'll give me a better idea. If we start with 1, that should be fine. So that'll be great. All right, so here's the original series. And it's kind of interesting because if you'll notice, there's sort of a little bump here at first. So the series goes up, and then, I'm sorry, the sequence values go up in number, and then it starts decreasing. All right, so that's a little bit strange. If we look at sequence B, that doesn't happen, but ultimately it doesn't really matter what happens with the first few terms as long as a pattern continues from there forward. Now, what we'll notice here is that these values are fairly distant from one another. And usually when we got a result, we had these values of the sequence terms like almost on top of one another. And that is what's necessary for us to get a result with the limit comparison test. We need those individual values to be really, really close to one another. So they need to be going to 0 at approximately the same rate. If they're going at a much different rate, then we don't get a result. So let's take a look at the limit comparison values. So if we divide these two together, all right, when these values are very different from one another, their ratios will tend to either increase or go to 0. And so that's when we don't get a result in the end. So when I use the limit comparison test, it's generally reserved for things that I know are going to go to 0 at approximately the same rate. So like for instance, anything involving polynomials, I almost always use the limit comparison test for. Occasionally with something that's very similar to a geometric series, I might use a limit comparison test, but I tend to make sure I always restrict to the limit comparison using when polynomials are involved at all. So like a rational function, that is. All right, so can we determine what's happening with this particular series? Well, we certainly aren't going to get very far with the limit comparison test, so it might actually be something we would need to use a different test for. It's possible that it would work with the direct comparison test. Let me get rid of this and zoom back out a bit. So here's the thing. If I were using the direct comparison test to 1 over n squared, so this is my known series with the red line. So it's going to 0 fast enough to converge. The blue line would need to be going to 0 even faster in order to prove that it converges. So it doesn't look like it converges. If we made that comparison to 1 over n, the harmonic series, let's see if that changes things. All right, so 1 over n, okay, so that's known to diverge. So what we would need then is all the terms of this other sequence, the one that's not known, to be larger than those. But unfortunately, this is still less than these. So it can't be proven to converge or diverge with the direct comparison test either. So it's possible that we could use like an integral test or maybe some test that we haven't seen yet. We'll probably come back to this example a bit later, but for now it looks like we'll just have to take the result that the test has failed. All right, and that's going to happen from time to time. You're going to apply a test and it can fail, and then you just have to find a different test to use in order to finally get a result. A little bit later, I'll give you some advice on how to choose the most appropriate test, but we need to get through all the different tests first. So, all right.